everyone, I'm Maria Victoria Amigo Samagang and I'll be presenting our work entitled A P-Graph Approach for Planning Sustainable Rice Straw Management Networks. This work is authored by myself, an assistant professor from the University of the Philippines, Los Baños, and currently a PhD student from the De La Salle University, and Professor Mike Promentilla from the De La Salle University. The presentation is divided into 4 parts, and we will begin with the introduction. There is an abundance of rice straw globally, and it's commonly dealt with by open field burning. But this practice increases the particulate matter and polyaromatic hydrocarbons concentration by a number of times, threatening human health and biodiversity. On the other hand, best rice straw management can lead to sustainable byproduct development and reduce pollution. Rice straw has many alternative value-adding uses such as bioenergy, animal feed preparation, and mushroom production. Each stage in the rice straw management, beginning with the rice straw collection, storage, transportation, pre-processing, and utilization, has different alternatives, forming a network of options with varying energy requirements and costs. Such systems can be optimized using process integration tools so that the raw materials are used efficiently at the maximum profit and with a minimal carbon footprint. The P-Graph framework is an efficient process integration tool that solves process network synthesis problems such as in rice straw management networks. A P-Graph is composed of a bipartite O-type node and M-type node vertices. It is based on 5 axioms and operates on 3 main algorithms. We have the maximal structure generation, solution structure generation, and accelerated branch and bound. P-Graph finds the optimal and near optimal solutions for further analysis, which is useful in decision making. P-Graphs have been widely applied to various fields, including solving environmental and economic problems. A number of studies have been found on P-Graph networks using agricultural wastes. For example, a study used P-Graph in the synthesis of sustainable energy supply using agricultural wastes as fuel, and P-Graph was also used in optimizing agricultural waste-based integrated biorefinery or IBR processes. And on the right, we have the maximal structures of the P-Graph models of these mentioned studies. P-Graph framework has been applied to optimize bioenergy systems using agricultural wastes. But so far, no studies have been found optimizing rice straw networks considering non-bioenergy products. In addition, literature studies do not consider the straw collection and storage steps of rice straw, which are energy and cost intensive. To address this research gap, the current work developed a P-Graph model of rice straw management networks, considering collecting, storing, and producing non-bioenergy products such as fodder and mushroom, in addition to bioenergy products. The model's performance was illustrated by a case study. Disruption scenarios considering reduced raw materials were investigated. Moving on to the methodology. The formal problem statement is stated as follows. Given the raw materials, which are rice straw, diesel, and labor, and various final products, which are the pellets, mushroom fodder, biogas, biochar, and heat, with their corresponding process teams data, which are the unit cost, unit price, availability, etc. Given the various operating units, which are the balers, tractor, storage, pelletizer, fodder pretreatment, anaerobic digester, pyrolyzer, and furnace, and their corresponding techno-economic data and input and output rates. The problem is to find the optimal and suboptimal allocation of the rice straw in terms of maximum profit. The maximal structure of the P-Graph model was constructed using the software P-Graph Studio. The brown lines represent the diesel requirements of the processes, while the green lines represent the manual labor requirements. The following slides show the data used in this work based on published literature. Rice straw, diesel, and labor as raw materials were considered as they are the main source of energy and energy consumption and cost of production. So we have here in the table the raw materials and the final products and the unit costs of each, and also the availability for the raw materials. This is the techno-economic data of the operating units. Examples of the operating units are the baler or the machines used for collecting rice straw. Storage is also considered since it also has cost. Then we have the pelletizer and other operating units. Then we have the input and output rates of the operating units, including the raw materials, fuel, and manual labor. This is just a continuation of the data. 4 scenarios were investigated. The baseline scenario assumes 3 different rice fields with a total rice straw yield of 96.84 tons per year and unlimited diesel and manual labor. Scenarios 2 to 4 are disruption scenarios wherein the availabilities of diesel, manual labor, and rice straw are reduced to 100 liters per year, 500 megajoules per year, and 75.32 tons per year. Next is the results and discussion. Based on the results, the optimal solution is mushroom production with a profit of over 14,000 USD per year, followed by rice straw pellets production with a profit of over 12,000 USD per year. And among the top 10 solutions, only mushroom production and rice straw pellets are selected. We can see on the left part of the table the amount of diesel, labor, and rice straw needed to achieve the final product and profit. This slide shows the structures for the top 2 optimal solutions as well as the 19th solution. So the top 1 solution is mushroom production and the top 2 solution is straw pellet production. Further production only comes in 19th place with a profit of over 7,000 USD per year. For the other unique solutions, we have biochar combined with heat for paddy drying, ranked 29th with a profit of over 5,000 USD per year, while baled straw and heat for paddy drying is ranked 52 with a profit of over 3,400 USD per year. Biogas production is not selected among the near optimal solutions. Moving on to the disruption scenarios. In the first scenario, a limit of 100 liters per year in the diesel was imposed, simulating future decarbonization. The results show that reduction in the available diesel favor mushroom production, completely removing pellet production from the top 10 solutions. And the maximum profit is reduced to just 4,000 USD per year. The second scenario reduced the available labor to 500 megajoules per year, simulating the lack of interest of the future generations in agriculture. In this scenario, the optimal solution is still mushroom production, with the same profit as the baseline scenario of over 14,000 USD per year. Pellet production is also among the top 10 year optimal solutions, but accompanied by baled straw sale with a total profit of over 10,000 USD per year. The third disruption scenario assumed that rice straw in field 1 is unavailable, simulating the possible land use change. And we have here the results. It's still mushroom production and rice straw pellets production at a reduced capacity. Moving on to the conclusions and future work. A P-graph model for rice straw management network was developed considering collection and storage of the rice straw and production of non-bioenergy products. The model can generate optimal and near-optimal solutions based on profit and can simulate raw material disruption scenarios. Based on the illustrative case study, mushroom production is the optimal solution in terms of profit, followed by pellet production. Disruption scenarios at reduced diesel, manual labor, and rice show that mushroom production is still the optimum solution, showing the robustness of the solution. This basic model demonstrates that P-graph can be applied to rice straw management networks to aid with the decision-making for sustainability. Future work includes carbon footprint accounting, integration with multi-criteria decision analysis, techniques to evaluate the near optimal solutions and considering demand constraints and uncertainty in the data. We have now reached the end of the presentation. Thank you very much.